Hello, good morning, good afternoon, good evening. I'm not sure what time it is when you're watching this anyway. The topic is I want to talk a little bit more about sizes of atoms, sizes of ions, how that relates to ionization energy, electron affinity, and finally something sort of new, electronegativity, and how we'll use electronegativity to gauge the lopsidedness of a bond, the polarity of a bond, the degree of ionic or degree of covalent nature to a bond. I won't get into all that in a whole bunch of detail today, but in any case, let's rewind the clock just a little bit into our third unit where we talked about periodic trends. If you'll remember, this is a little bit blurry. Let me go down to the next one. This next one's a little bit more clear. I like that one. There we go. If you'll remember, we talked about how, can I make this bigger? Yeah, a little bit. That's too big. Is that too big? That's just a little bit too big. I apologize. Let's just try that. Stay with that. If you'll remember, as I go down a column, a group, a family in the periodic table, the atoms and ions invariably get larger because they have an increased number of layers of electrons. Doesn't matter where on the table, on the metals, on the non-metals, even the noble gases, same story. The atoms get larger. I think these are in angstroms, if I'm not mistaken, radii in angstroms. Yeah, so the smaller atoms are further up and to the right. Yeah, as I go down they get larger. Oh yeah, the other trend was a little bit confusing, counterintuitive a little bit. As you go to the right, the atoms also usually get a little bit smaller. Because this is a little bit smaller than this because an increased number of protons in the nucleus pulling on the electrons at approximately the same energy levels pulled that atom into a smaller sphere and also pulled the ions into smaller spheres. Interesting. Okay, so what did that mean about ionization energy? As I go down a family, the ionization energy decreases. It gets easier to remove an electron because those electrons on the outer valence shell are further from the nucleus, feel less of a pull from the positive nucleus. On the other hand, as I go from left to right, the ionization energy increases, again because usually overall the atoms and ions get smaller and smaller. Radii mean the valence electrons are closer to the nucleus, more attracted to the nucleus, and therefore harder to remove. So ionization energy increases as you go left to right. We also talked about electron affinity, the energy usually given off when an atom gains an electron. We said that fluorine and oxygen and chlorine very much stabilize when they gain an electron. So electron affinity, very greatly negative. Negative meaning that they give off a whole bunch of energy when they gain an electron. But down here, not so much so, especially the metals. Most of the metals don't really want to gain electrons, so the electron affinity is small, albeit usually a little bit exothermic, a little bit negative. In just a second, we're going to combine those two ideas into something new called electronegativity. Before I do that, though, do you remember the trends? How would I rank these? I see nitrogen 3 minus, nitride, oxide, fluoride, fluorine gaining 1 electron, oxygen gaining 2 electrons, nitrogen gaining 3 electrons. This is just for pretties. These all have 10 electrons. 10 electrons. Nitrogen had 7 protons, 7 electrons, but if it gains 3 to become a nitride ion, it now has 10 electrons. And 10 electrons, 8 plus 2 and 9 plus 1 is 10 electrons. 10 electrons is just like neon in electron configuration. But fluorine has 9 protons in the nucleus, 8 protons in the nucleus, 7 protons in the nucleus. So which nucleus, being positive, pulls on its 10 electrons, 10 electrons, 10 electrons with more oomph? The answer is fluorine. So if you're pulling, because it has more protons in the nucleus, pulling on those 10 electrons, not 10 valence, 8 valence, pulling on those electrons with more strength because you have more protons in the nucleus makes the ion smaller. We're supposed to rank these from smallest to largest. So I guess I'm going to have to go fluorine's the smallest, followed by the oxide. It has 8 protons in the nucleus, 10 electrons, 7 protons, 10 electrons. So as I go from fluorine, oxygen to nitrogen, fluoride, oxide, nitride, they would get larger because the protons in the nucleus can't pull the nitrogen, nitride, into as small of a sphere as the fluorine. Excuse me. Alright, another similar question. Here's what we call an isoelectronic series based around argon, I could say. Argon has, excuse me, clear my throat. Yeah, argon has 18 electrons. Chlorine had 17 electrons, but if it gains one to become chloride, then it gets 18 electrons. Sulfur has 16 electrons, but if it gains 2 more, it gets 18 electrons. So all these species have 18 electrons, which is a noble gas electron configuration, so they're all very stable. But isn't it true that calcium has 20 protons in the nucleus? Losing 2 electrons brings it down to 18 electrons, just like argon. But 20 protons in the nucleus pull this conglomeration into a smaller sphere. So if I want to rank them from largest to smallest, I'm going to go calcium 2 plus is the smallest. Oh, that's probably it right there. It's the only one that has calcium 2 plus the smallest. Followed by 19 protons, 18 protons, 17 protons, 16 protons in the nucleus, all pulling on those 18 electrons. So choice 5 ranks them from the largest to the smallest. Interesting. Oh, here's another one. If you want another one, oh, argon, chlorine, yeah, another isoelectronic series. Iso means the same, electronic, electrons, same number of electrons. We could rank these from the smallest to the largest as well. Again, because strontium has 38 protons in the nucleus and now 36 electrons, those are pulled into a pretty small sphere. I suppose the strontium ion is fairly chemically unreactive. I think I just did that thing I had written in brown there. That's redundant. Sorry about that. Alright, so now we're going to combine electron affinity and ionization energy in some kind of man-made construct called electronegativity. Usually for electronegativity we ignore the noble gases because they don't react very well at all with anybody, so we leave them off. Let me define it. I haven't written this down. Maybe I should. Maybe you should. Maybe you can Google it. It goes like this. Electronegativity is the tendency or ability of an atom to pull electrons towards itself when it's entering into a chemical bond. That could be an ionic bond or a covalent bond if you know the distinction. If you don't worry about it. But it looks like fluorine is the champion of electronegativity. It's very close to 4.0. Oxygen's pretty close as well, down to 3.44. Chlorine's pretty strong at pulling electrons as well. It seems like these electrons with highly negative electron affinity, did I say that right? These atoms, these elements that are very small in size have a great electronegativity. Small atoms do have a great ability to pull electrons towards themselves when entering into a bond. Notice hydrogen in this particular construct, this table, whoever made this table, put hydrogen here and here, which I've seen done many times. It's arguably an interesting thing and sometimes a good thing to do. But as I go further down and left, down to cesium, strontium, or even the metals in the middle, the transition metals, they have lower and lower and lower electronegativity. They can't pull electrons toward themselves. As a matter of fact, they're often called electropositive. Like aluminum is not very electronegative, therefore it's electropositive. Potassium, 0.82 on the scale of electronegativity, so it's not electronegative, it's electropositive. Curious. Don't worry about that. But memorize this. Fluorine, chlorine, oxygen, sulfur. And the further up and to the right you go, the more electronegative. And the more electronegative, the more able you are to pull electrons toward yourself in a bond. So, sometimes we'll do this. Sometimes we will compare two elements on the table and say, well, if these two elements are entering into a bond, what type of bond are we talking about? We can actually look at these numbers and do some subtractions, and I've seen it done that way before as well. But on a simple basis, so let's say if the elements are different, there's a very good chance they're different in electronegativity. And if they're different in electronegativity, the bond is polar or lopsided, or they're not an even sharing of electrons. And if you get them really far apart, like take something from the metals and something from the nonmetals, like oxygen and titanium, or strontium and sulfur or chlorine. If they're very far apart physically on the table, that probably likely means they're very far apart in electronegativity. And the further apart they are in electronegativity, we say their bond is more polar, or their bond has a high ionic character. On the other hand, if you took two elements that were close to each other on the table, like sulfur and oxygen, or nitrogen oxygen, or nitrogen chlorine, or even chlorine and fluorine can sometimes bond. Two elements that are close to each other on the table, the difference in electronegativity is small. We say that they have a high covalent nature, a high degree of sharing electrons, not very much of a transfer of electrons. So ionic bonding, very far apart, is a transfer of electrons. Covalent bonding, where the usually nonmetals are close together and they're sharing electrons, that's called a covalent bond. A polar bond, a slightly polar bond, a not very polar bond. But even if I took, let's see, oxygen and chlorine, or oxygen and nitrogen, they're pretty close to each other on the table. They're still sharing. It's still, like, they would call it a covalent bond, but it's not perfectly purely covalent, because there's a slight difference in electronegativity between the two. On the other hand, if I had two oxygen atoms sharing electrons, that would be a purely covalent bond. Or two chlorine atoms sharing electrons, purely covalent bond. Or two hydrogen atoms sharing. So if you had two atoms of exactly the same electronegativity, or indeed they're exactly the same, then the bond is purely covalent. They're sharing perfectly well. So if I look at a scale, going from a difference in electronegativity from 0 up to 3 or 3.5 or something, the greater the difference in electronegativity, the more ionic character there is to the bond. It says here the percent of ionic character. But if my elements are close in electronegativity, and the difference, like literally subtract the numbers and get a small difference, then we say that there's a low percent or low degree of ionic character, a high degree of covalent character. Interestingly, HF is about smack dab in the middle. Alright, that's enough now for now. Go relax and have a drink of something. See you in a bit.